wanted to start with a big thank you to Energy Trust of Oregon for not only sponsoring this grant, but also just the support from Kriya and Naomi and Kelly along the way. They've also put together a team of experts in the industry to review this research, so it's all just been super helpful and I think made the work better. So a quick outline of what I'm going to be talking about today. I do want to mention that I'm going to be talking about some kind of foundational items, laying the groundwork for the actual research. So be patient. I will get to these case studies. That's really the heart of the research, but I'm going to start with some other topics. So a little bit about the team, and I'll start with a little bit about me. I've been a practicing architect in Portland for over 30 years now. You know, I've had the privilege in that 30-year career of working on many different project types, many different scales. And about 15 or 16 years ago, I read a little bit about Passive House and became very interested in it. And in 2012, I took the training. I became a certified Passive House consultant. And then in 2013, I completed my first certified Passive House project, which was also one of the first certified projects in the Northwest. And it also happens to be my own home. In addition to me, I got a lot of support from some other folks. Forrest at PAE Engineers, he was responsible for the energy modeling. A former colleague, Johan, was responsible for all the embodied carbon modeling, and then some other colleagues, Shakari and Alyssa, helped with some of the data visualization and graphics. So team effort. So Lever Architecture was formed in 2009, and you're seeing here the Albina Yard project. This project was completed in 2016. This was the first building in the US to be completed with domestically sourced CLT mass timber. This is also our Portland office, and we also have a small office in Los Angeles as well. So a quick map and timeline looking at past and current Lever mass timber projects, and these are all within a 3-mile radius of our office, which is pretty amazing and exciting. And we're also working on mass timber projects from California all the way out to Portland, Maine, and a few stops in between. And we're currently in the design phase of our, what will hopefully be our first certified Passive House project as well. So a little intro about the research and why this research. I think there's certainly an urgency to rapidly decarbonize to avoid more climate change or drastic climate change. And we wanted to understand the relationship of energy efficiency and low embodied carbon and what the synergy, connection, how those impact each other. Low-rise wood buildings are certainly still the most prevalent construction type. So we wanted to look at some pros and cons of mass timber versus stick frame buildings. We wanted to understand some key decisions to help make low carbon wood buildings. And then finally, we asked the question, is it even possible to build a net zero carbon building? So I think, Kriya, we were gonna maybe do a little poll now.
Yes, absolutely. Let me pull that up right now.
Okay.
And launch it.
Great. And I'll just keep going while we're doing that. I wanted to provide a little visual context. Hopefully everyone here is pretty familiar with mass timber and stick frame, but for some visual context, a couple of mass timber projects, the one on the left is showing some cross-laminated timber, load-bearing walls, facade panel, and then
Jeff, we have the quick poll open for people now, so
okay.
We'll come back. It will be nice to relook at the visuals after this. The polls for everyone, Jeff's poll, which I think I'm just as curious as everyone else. Please indicate if you've been involved in the design and or build of and you can pick more than one, all that apply, a certified passive house project, a mass timber project, or the great combination of a mass timber project that is also certified as a passive house. So we're collecting responses right now. We have about 50% of our audience having already voted, and I'll give maybe a couple more seconds for people to engage. And then curiosity is growing. Let's find out. All right, Jeff, what we're seeing in our poll today is 21% have worked on a certified passive house project. Almost half of our audience has worked on a project that has dealt with mass timber, and only 2%, a very rare group, have done both mass timber and it's been on a certified passive house project.
Okay, that's amazing. That's great to know who I'm talking to here. Right.
And we are back with you and your image of the mass timber, the two projects.
Okay, great, thank you. So again, to provide a little bit of visual context for those who aren't as familiar with mass timber, on the left, a project using cross-laminated timber, load-bearing walls, cross-laminated timber facade panel. You can see the cores in the background, and then some floor panels going up on the right, an office building using a glulam column and beam structure with cross-laminated timber floor and roof panels spanning those. And then, of course, the ubiquitous stick frame building on the left is what we refer to here as a 5/1 or a podium building with wood stick frame construction above a concrete podium. And on the right, an aerial photo showing some floor framing in progress, all those little sticks getting cheap. So that's the context. So the research questions that we wanted to ask is which wood structure between stick frame and mass timber has the lowest embodied carbon? Is there a clear distinction or a clear winner? What assemblies are required to meet passive house? This project or these case studies are located in Portland, so we're talking about climate zone 4C here. How do mass timber and stick frame assemblies compare, specifically the passive house assemblies? And then what assemblies have lowest embodied carbon? Are there some distinctions and some clear winners? And when is mass timber more appropriate than stick frame? And then finally, again, is it even feasible in today's building climate to build a zero carbon building? So the methodology, we're going to use we've used three case study projects. Step one, we're going to do some energy modeling to determine the R values of the assemblies required to meet passive house. We're then going to do some embodied carbon modeling to estimate the carbon from those resulting buildings. We're going to then look and determine the biggest PV array that we can locate on the building, on the site, ideally to achieve net zero carbon in 25 years. That's kind of our goal. And then we're going to evaluate all the embodied carbon calculations and provide some strategies and recommendations. So the project we're using, or we've used as a case study, this is the Williams and Russell development. The site is the former home of the Hill Block building, which in the mid 20th century was really kind of the heart of the Black community in Portland. In the early 1970s, there's a hospital just located to the upper right, out of view in this aerial photo. That hospital acquired through eminent domain in the early 70s this property for a future expansion of the hospital. They raised all the buildings and the expansion never happened. So this site has unfortunately sat empty since then. Fast forward to today, and this amazing group of Black Portlanders has been working with the hospital to get the land donated back to the community and then to develop this this new future hub or heart of the community here. So what you're seeing, these three projects on the lower right, this is a 24-unit townhome development. These will be for sale, affordable townhomes. On the left is a 4-story, what we're calling the Black Business Hub. It's really a kind of an incubator office building. It has micro retail on the ground floor, a variety of office types on the upper floors designed for Black-owned businesses. And then in the back is an 85-unit affordable rental apartment project. So those are the 3 case study projects. So again, a little background. We're gonna just talk briefly about carbon, the language of carbon, why carbon. Of course, buildings are responsible for, approximately 39% of global carbon emissions. Carbon is a universal metric. Carbon allows us to estimate the full impact of emissions from construction, and most importantly, the emissions from not just the buildings, but the supply chains, all the material that's going into the building. So there's a number of names that are used pretty interchangeably when you talk about carbon, carbon dioxide, CO2 emissions, equivalent, greenhouse gas emissions, GWP or global warming potential. These are all kind of referring to essentially the same thing in this context. So total carbon, when we talk about total carbon, what we mean is embodied carbon plus the operational carbon. Embodied carbon is comprised of a number of different sort of stages. Those include the extraction and production of the materials that are going into a building, the actual construction, maintenance and repairs that happen during the use of the building, and then of course the end of life, whether that's demolition or deconstruction. Operational carbon, of course, is the emissions from operating a building, heating, cooling, lighting, appliances, plug loads, etc., hot water, all those things that we're familiar with. So it's important to understand or talk about the time value of carbon. And so really this idea is to limit global warming and avoid major climate change. We want to reduce emissions today, and that's kind of more important than future emissions. That's what the time value of carbon is saying. So, one approach is this total emissions approach, where you're selecting strategies that really emit the least amount of carbon over a building's lifetime. And in some of those cases, if we're talking about maybe more insulation to reduce operational carbon, it might result in increased upfront emissions. And then the flip side of that is to say upfront emissions are what are most important. We want to reduce upfront emissions, even if it means we're going to increase carbon emissions over the life of the building from operational carbon emissions. So again, when we're talking about carbon and we're talking about embodied carbon, there's a number of different stages that make up embodied carbon. So if we look at the big box, the big blue box on the top, that's kind of the full, what we consider the full life cycle of embodied carbon. And that includes product stages, extracting the materials, manufacturing materials, building the building, the construction, and then it also includes, repair, replacement, and then the end of life. So that's a more comprehensive look at embodied carbon, but it's also much more difficult to predict, especially the use and end of life stages, and therefore it's just tends to be far less accurate. If we're looking at only the upfront carbon, it's certainly a more limited look at those stages, but it tends to be much more accurate. And then again, when we're talking about total carbon, we're including operational carbon or operational energy, and we've really become quite good at estimating that accurately. So I'm going to do a quick Passive House primer in 3 slides. Sounds like there's a lot of Passive House experienced folks on the call, which is great. So why Passive House isn't net zero enough? On the left, This graph is looking at a code minimum building and sort of typical seasonal loads. Heating energy, you've got these high peaks of heating energy in the wintertime. You've got a pretty high peak of cooling energy in the summertime. And when you think about renewable energy and the production of renewable energy, especially in our climate, it tends to be highest or producing most energy in the summertime, the least amount in the wintertime, and that's certainly a mismatch with those seasonal loads. So what Passive House allows us to do is really reduce those seasonal loads and to make at least a much closer match to our on-site renewable energy. So Passive House, there's essentially 3 main performance criteria with Passive House. It's different from other certification programs. There's not a checklist. It's either pass or fail. You have to pass all 3 of these requirements. They're thermal energy demand, which is really your annual energy demand for heating and cooling. There's total energy demand, which includes all of your electrical systems, devices, and then there's an air tightness requirement that's quite aggressive or ambitious. So there's specialty modeling software that's used to model Passive House. The input is extremely detailed. And what's really important for this discussion is that the assemblies are material agnostic, meaning it's the effective R value that's most critical, not just the R value of insulation that's, for example, filled in a cavity. It's really how that whole assembly performs. So Passive House principles, I mean, these are really just good energy efficiency principles. I won't talk much about them other than to kind of summarize them. You know, you typically see super insulation, thermal bridge-free construction is very important, especially in Passive House because they're really scrutinizing all of that thermal bridging. Again, airtight construction with mechanical ventilation and heat recovery. You know, good, really high performance glazing, suited to, again, all of these are suited to the climate and suited to the building type. And then, you know, efficient equipment, efficient distribution of that mechanical equipment. So it's also important to talk about wood when we're talking about carbon accounting and embodied carbon. So biogenic carbon or sequestered carbon is kind of a hot topic in embodied carbon. So the way it typically works in most carbon accounting is that you see a negative value for your upfront carbon, and then that is offset with emissions that occur at the end of the life of a building. So the total embodied carbon has this kind of plus, this -1, +1 accounting of carbon from biogenic carbon or sequestered carbon. And so with that, I would say there's a pretty high degree of uncertainty in the modeling, and there's a lot of people who are really looking in more detail at this issue and how better to model biogenic carbon or understand biogenic carbon. So if we're looking at just upfront carbon, you're receiving a credit for that sequestered carbon, but you're really ignoring the future emissions that are going to happen at the end of life of a building. So we've talked before about the time value of carbon, upfront emissions, reducing upfront emissions is really critical, but I think the risk here or the issue is that we could be incentivizing the use of more wood or more materials that sequester carbon. So many people will argue the most conservative approach is just to not include biogenic carbon or ignore biogenic carbon. I think at least it's important to always identify if it is or isn't included. And so you're going to see here, in many cases, we are including biogenic carbon, but we're always going to say if it's in or not included. Another important aspect of wood in carbon accounting is that wood environmental product declarations, wood EPDs that are used in the calculations, they represent an average. So they don't distinguish between wood that's sourced from a specific forest, a well-managed forest, a business as usual forest. So all wood in EPDs is represented equally. And so this graph, what it's showing is that in reality, the embodied carbon of wood that's coming from different forests potentially has a wide-ranging difference in its embodied carbon. You see at the top, there's some wood products that are coming from certified forests that have pretty low embodied carbon values. You can see the average, and then you see at the bottom, there's some wood products coming from business as usual forests that are actually have more embodied carbon than steel or concrete. So it's important to know your source of wood and understand that all wood is not equal. All right, so on to the case studies. The three projects, again, are the townhomes, Black Business Hub, affordable apartments. I think the key for these case studies is that you have projects that vary in scale from around 30,000 square feet up to almost 100,000 square feet in the apartments, and they range in height from 2 and 3 story up to 6 story. And then there's a range of construction types, which I'll talk about briefly later. So a view of the townhomes from the street. This is, again, 24 units. It's actually divided into 2 identical buildings with a small gap between them. There's this drive to the north. All of the entries into the houses are on the north side or plan up in this view. And again, they vary between 2 and 3 stories. So a quick summary of the operational carbon. On the left is a little chart showing the difference in the various components for the modeling between a code minimum passive house. It's not really important here to be able to distinguish between those. On the right are 2 graphs showing the annual operational energy on the left, and those are, the darker one is code minimum, the one on the right and the lighter green is passive house version. And on the right, those are just converted into kilogram CO2 so that we can use those to evaluate total carbon later. And really what's most important is that the passive house achieves about a 47% savings, which is pretty significant. Broken down, the envelope improvements result in about a 13% savings. The systems have much more impact at a 34% savings. So here's some section views of the assemblies that we used in this modeling. On the left, vertically is the code minimum assemblies. Across the top is roof, middle is wall, bottom is floor. And then on the right are the 2 different versions of passive house. In the middle is mass timber. On the far right is the stick frame. So a couple of highlights, things to take note of. The mass timber version, when we look at the roof, that's using all of its insulation outboard of the mass timber. So it's therefore using a foam insulation in this case is our assumption. That's the most common assembly. The stick frame version is using a vented roof cavity with cellulose insulation. So a really deep truss with cellulose insulation. Looking at the walls, again, the mass timber version, all of its insulation is outboard. Here it's assuming mineral wool insulation, which is pretty common. The passive house stick frame version has a stud cavity with cellulose insulation and a small amount of exterior mineral wool insulation. And then looking at the slabs, code minimum, there's no insulation. The passive house versions both use foam under slab, 3 inches of XPS. So here's just a kind of an axonometric view of the assemblies pulled apart for the mass timber and stick frame. It's a little bit hard to decipher here, but one important thing is that the stick frame just tends to have a lot more layers than the mass timber. The mass timber tends to be simpler with fewer layers. Another point, and this is really related to a vented roof in a passive house stick frame assembly versus an unvented roof in the mass timber is there's kind of a tricky transition of that critical air barrier from the wall to the ceiling or to the roof, much more complicated in the vented roof of a stick frame version than the mass timber version. So now looking at the embodied carbon, one of the key things to note here is that on the left, we're looking at the upfront stages only. So the dark green includes biogenic carbon. The lighter one does not include biogenic carbon. So again, when we're looking at upfront stage only, and we're including biogenic carbon, we're getting the credit for that sequestered carbon without seeing the future emissions. The mass timber has most wood in it, and therefore it has by far the lowest embodied carbon, even negative. On the right side, we're seeing the full life cycle stages, so all stages A to D. And there, when we look at the mass timber, even including the biogenic carbon, because now we're counting the emissions in the future, because it's using more wood, that actually has the highest embodied carbon of any of the versions. And the stick frame, in this case, has lower embodied carbon. So now we're seeing a little breakdown of the major materials, the embodied carbon in these major material groups. Concrete, all three are the same. There's no change between the schemes. Same with steel. When we look at the breakdown in wood, now this is again full life cycle. It is including biogenic carbon, but the mass timber is using far more wood. Therefore, it's using, or it has far higher embodied carbon. And then we look at the insulation. Again, the mass timber version is using more foam, more mineral wool, tend to be higher embodied carbon materials. Therefore, it has the highest value. And then for reference, there's a few different PV array sizes, which I'll touch on in a minute. And you can just see the relative embodied carbon compared to some of the other major material groups. So now we're looking at on-site renewable energy. So this was a pass kind of for fun to see a code minimum building, how much PV is required to get to net zero, just to get to net zero energy. So the outline of the buildings are in blue. This project has kind of this on-site parking to the north. So there was an assumption maybe we could provide a canopy above those parking spaces, but you can see in green the amount of PV array needed to get to net zero energy for this code minimum building far exceeds available rooftop, available parking, canopy area. So pretty significant. Here's two versions that are maybe a little bit more achievable. So on the left is actually our current scheme. So this is just putting PV on the buildings only and only on the south half of the building. This is 116 kW PV array, and it gets us to about 60% net zero energy. If we were to say suspend our current disbelief or forget our current scheme and look at what's possible if we increase the PV array on the buildings and took advantage of canopy above parking spaces, 216 kW PV array would actually, with passive house, would get us potentially to net zero carbon in 25 years. So what does that mean on the left? This is that 116 kW PV array. The green is the annual operational carbon. So you can see that's climbing each year because we're not to net zero, we're 60% of net zero. And then in the pink is the total upfront carbon. And so this includes the building plus the embodied carbon from the PV array. And so that's what that pink represents. Then on the right is a stick frame passive house with the larger PV array. And because that PV array is larger, it has more embodied carbon. You can see the pink line is actually higher. But that bigger array allows us, in theory, to be energy positive on an annual basis. And in 25 years, we're generating enough additional energy to offset our embodied carbon, in theory. So the next project is the Black Business Hub. So looking at the plans of this, this is a pretty simple rectangular building. It is made slightly more complex and maybe a little less efficient because at the ground floor, one of the desires was to have this gap in the building to allow the public to flow through. And on the left on this site will be a public plaza planned. So that connection was really important, but that does make the building a little less efficient. Also at the upper floors, there's some little recesses that you can see for some roof terraces. So when we look at the operational carbon summary for this project, with the envelope and systems, again, you're seeing about a 48% savings of Passive House versus code minimum. The envelope savings, about a 14% improvement, and the system's responsible for 34% of that. So the section views of these assemblies are actually a little bit more similar. There's a little bit less distinction between the code assemblies and the Passive House assemblies. You can see at the bottom, none of the slabs are assumed to require insulation. So even the Passive House versions can meet Passive House criteria without under slab insulation, again, for this building type, for this climate. The wall assemblies, similarly, the mass timber version has all outboard insulation. But in this case, for the roof assemblies, we assumed both the stick frame and the mass timber used an unvented roof assembly, which is much more common in commercial construction. So they both use foam. The mass timber one is 5 inches. The stick frame version has 6 inches. And the code version also has 5 inches. So again, they're all pretty similar here once you're getting bigger in scale. So one of the things planned for this project is a below grade parking structure. So we really wanted to look at what's the impact of that below grade parking structure. So when we do that, it results in an estimate of about 170,000 kilograms of CO2, which is pretty significant. This is more upfront CO2 than the entire mass timber building. Again, just looking at upfront CO2, counting, including biogenic carbon, and it's more upfront CO2 than a pretty large, significant 273 kW PV array. So on the right, you can see it accounts for almost 2.5 times the carbon as the mass timber building itself without it. So these versions are excluding that below grade parking. Again, on the left, we're looking at upfront carbon only. On the right, full life cycle. Similar to the townhomes, when we just look at upfront, the mass timber version is by far the lowest. But then when we look at the full life cycle, mass timber has more wood fiber, has higher embodied carbon. So again, a breakdown of the major materials. For the concrete, you see a little bump for the mass timber version, and that's because we modeled the mass timber office building with concrete topping slabs, which is a pretty common strategy for acoustics, vibration, also routing of utilities. Steel in all versions is pretty similar. Again, when you look at just the wood, mass timber uses far more wood, so it has much higher embodied carbon. Insulation is a similar result, a little bit more foam, more mineral wool, therefore it's higher. And again, just some relative comparisons for a variety of PV array sizes. So like we did for the townhomes, what does it take to get a code minimum building of this scale to net zero energy? a huge PV array that far exceeds any available roof and site area. So then two options. The option on the left, again, is like with the townhomes. This is what's currently planned in this concept design. It's roughly an 82 kilowatt PV array, 30% net zero energy annually. And then on the right is showing if this project were built to passive house, what it would take to get to net zero carbon in 25 years for a mass timber version. And again, this is just looking at upfront carbon and including biogenic carbon. So you can see it's still a pretty ambitious PV array size, probably not realistic. It's covering much of the site as well as the building. And again, just some graphs showing what that means. On the left, you can see we're 30% net zero energy annually. That green bar representing the annual operational carbon is very quickly outpacing the embodied carbon project. On the left is showing an energy positive version with an unrealistically large PV array and gets to net zero carbon in 25 years. So I think you could argue that it's pretty challenging in this scale of project to achieve net zero carbon in 25 years. So finally, affordable apartments. This is, of course, a bigger scale. This is planned as a six-story building. Some plan views. The ground floor has some amenity spaces. It includes a childcare and then some back house support spaces. And then all the upper floors are built with dwelling units and repeat as they move up the building. So the operational carbon summary here, I think what's probably most interesting is that as the building gets bigger and inherently more efficient, the savings from passive house are slightly less. So we get about a 33% savings overall, and the envelope savings or the savings from the improved envelope are limited now to about 7%. So some important distinctions when we talk about mass timber versus versus stick frame at this scale of project. On the right is what I'll call a conventional stick frame project. And the way these are typically done is concrete podium or a type 1 podium at the ground floor. This, at least in our building climate, is usually concrete. And then we're allowed to do up to 5 stories of wood framing on top of this, and this is fire treated wood. So the other option when you're looking at mass timber is to use the type 4C code, which allows mass timber to be used at all levels. So you can have any mass timber exposed at all levels, but any partitions that are either bearing or non-bearing all have to be framed from metal stud. So there's a little bit of trade-off there. You can eliminate the concrete podium, you get a lot of benefit from that, but any of your framed walls are metal stud. So when we look at this breakdown of materials, again, what's interesting when you look at the concrete on the far left is when you eliminate the concrete podium in the mass timber version, you see a pretty significant savings in embodied carbon. Similar to the other ones, the other versions, the other projects, the mass timber version uses more wood, therefore has much higher embodied carbon. I think the steel is represented as being the same for all projects. That probably needs a little bit more scrutinizing to understand the impact of eliminating reinforcing steel in the concrete, adding metal studs for all your partitions. And then insulation, again, the mass timber has a little bit more, but we're talking about a pretty negligible difference now at this scale. And then again, relative impacts of some different PV array sizes. So again, for fun, what does it take to make a code minimum building of this scale net zero? I think anyone who's looked at PV on a project of this scale, it's pretty impossible. This is showing an area that exceeds even the whole project development site. And then when you look at the amount of possible area, roof area, you end up with a 225 kW PV array, and which is about 18% net zero energy. So conclusions and strategies. Passive house assemblies, and again, we're talking about climate zone 4C. I think it becomes clear that as the building scale increases, the differences in the R value become pretty minimal. Compact, efficient forms result in simplified assemblies. This is realized at a larger scale, but becomes even more important as you get to the smaller townhouse scale. Deeper cavities, i.e. stick framing, tend to allow for more cost-effective insulation, so that fluffy insulation tends to cost far less, and it's possible to get lower embodied carbon insulation more easily. But continuous insulation better addresses thermal bridging. We didn't talk much about thermal bridging, but that is an important aspect of passive house. And then, yeah, air tightness thermal bridging can be the biggest challenges for passive house. So a little bit more about insulation. When we're looking at different insulation types, there can be a huge range of embodied carbon, and that's why I've sort of mentioned this idea about different cavity insulation versus an exterior insulation. So this is comparing a number of types of cavity insulation that's adjusted for the same R value for the same area. Highest is the upper left. That's a closed cell spray polyurethane foam. That's kind of an old legacy formula. To the right of that is a better, newer generation HFO closed cell foam. It's better performing. And then you move down to the lower right, which is kind of the best performing of these more commonly available materials, which is a cellulose dense pack, wood fiber, cellulose loose fill. Those are all bioproducts, and when you're looking at upfront carbon, they have a negative value. So comparing board insulations, your highest tends to be the old formula XPS insulation. In the pink in the middle is the reduced GWP formula, kind of the next generation of XPS that's more common. Again, these are working from upper left highest, the best at the bottom right, straw board at the bottom right, a little bit more esoteric, but has significantly lowest or negative embodied carbon. And you see wood fiber board currently not available in the US, hopefully will be available on the East Coast soon in this next year, and on the West Coast, hopefully soon after. All right, selecting the structural system, some advantages of mass timber, speed of construction, which we didn't really talk about. Your assemblies, floor assemblies in particular, tend to be thinner, so you can have a reduced floor to floor height. No concrete podium potentially required. And we haven't talked about it at all, but a really important one is the aesthetic qualities. Stick frame advantages, you get that cavity inherent in the construction for low carbon insulation. There tends to be less wood fiber. Those cavities can be used for services, which is certainly easier for planning. And it's because it's ubiquitous, there's no specialized labor, and it's easier to field modify. So some concrete reduction strategies. On the left, we're talking about a typical office building. If you can reduce or eliminate that topping slab, you'll realize some significant CO2 savings. Additionally, the wet assemblies, a concrete topping slab, tends to take longer to build and adds time to your construction schedule. Below grade parking, if it's possible to eliminate it, it has significant upfront carbon emissions associated with it, and it also, there's some unaccounted for or related aspects that also have embodied carbon emissions, and it will certainly lengthen the schedule of a project. Stick frame, again, the podium has significant CO2, so if it's possible to eliminate the podium, the trade-off for that is in a mass timber project, you're required to use this non-combustible metal framing. Of course, the aesthetics of exposed mass timber are a huge benefit, as well as speed. So I haven't really mentioned it. We've been talking about mass timber or stick frame. There are hybrid approaches that are very common. Stick framing, exterior walls, you kind of get all of those benefits. You have the ability to prefabricate those exterior walls with stick framing still. And then mass timber, floors and roof, you kind of get the speed, you get the aesthetic appeal. You can potentially use dry assemblies to enhance the speed and for low carbon. So maybe the best of both worlds in some instances. So what are the advantages of passive house? Why passive house versus code minimum? I think we've demonstrated it uses significantly less energy. It allows a smaller PV array to get to net zero energy and possibly on a small project to be energy positive. And then of course, there's comfort reasons, comfort benefits, and the projects are a passive house is more resilient to weather events. So what are some strategies for 2 to 3 story townhomes in particular? Build to passive house, use compact forms, stick frame. I think stick frame tends to be the more obvious solution for projects of this scale. Know where your wood comes from and try to prioritize, local sources, well-managed forests. Try to minimize the use of foam, other petroleum-based products, and use cellulose insulation if you can, use wood fiber insulation, and incorporate bio-based materials wherever possible. So for an office building, again, build a passive house. If you can eliminate the below-grade parking, that's a good strategy for reducing carbon. I think office building is probably the typology that lends itself best to mass timber, especially for the aesthetic opportunities, the flexibility in planning, and the speed. If you can use dry assemblies in lieu of the topping slabs, that's a great strategy. The hybrid approach where you're stick framing exterior walls allows you to maximize low embodied carbon insulations. And then similarly, minimize the use of foam, incorporate bio-based materials, know where your wood comes from. So for the larger apartment projects, again, build a passive house. You're going to find that your assemblies are pretty similar, not far off from code minimum, again, at least in our climate. If possible, look to eliminate the concrete podium. Again, there's trade-offs with that. Mass timber floors, floors and roofs, especially in a hybrid approach, can provide improved aesthetics and speed and reduced floor-to-floor height, which you really start to realize at the scale. Look to use dry assemblies, look to stick frame exterior walls. Again, this is that trade-off with the podium. And then similarly, incorporate bio-based materials, low carbon insulations, minimize your use of foam. So finally, some conclusions. Carbon modeling is really in its infancy, and I would say there are many uncertainties, especially when comparing wood buildings as we were trying to do here. I think the data accuracy is pretty challenging. We were using, in most cases, a pretty early conceptual building design, which makes it more challenging. Know the stages of embodied carbon when you're talking about carbon. Is it upfront? Is it full life cycle? I think that's very important. With that, be a little skeptical of zero carbon building claims. I think it's pretty easy to wordsmith your way around the data to make some claims that maybe aren't quite true. Understand your wood sourcing and that all wood is not equal. Look for verification of performance claims. Passive house strategies, while those high performance strategies are certainly important, but that's using those strategies is not the same as a certified passive house. And the whole is usually greater than the sum of parts. It's important to be thoughtful about your approach to every project and do all that you can to reduce carbon. Finally, I get a little bit of inspiration from this bio-based case study. This is a project outside of Paris. It's a nursery school. It was built with cross-laminated timber. It has prefabricated straw panels for exterior walls. It uses wood fiber insulation. All of the finishes of the interior are natural exposed wood, including wood windows, and it's Passive House certified. So certainly a great example. All right, thank you.